Hello, how are you? Welcome to this channel, which we call Medic Academy, where we study all various topics in the medical field, varying from medicine, nursing, physiotherapy, name it, all that you know. And here we host lessons and classes on different topics. So, welcome to our today's class, where we're going to do biochemistry but measuring on body buffer system. So, stay with me till the end. First of all, before we go into the deepmost of what we would like to discuss today, let's first introduce basic terms that we will be doing in each and every part that we'll be discussing the buffer system. So in our body fluids, that is the combination of intracellular fluids and extracellular fluids, we have acids and bases, or we have different concentration of we have different concentration when it comes to the components. So intracellular, by definition, this is fluid that is found within our cells or the solution that's found within our cells. And in the extracellular fluid, this is fluid that is found outside our cell. So as a reminder, intracellular fluid is found in the intracellular fluid is found in the intracellular compartment, and extracellular fluid is found in the extracellular compartment. So now in these compartments, or in these spaces where our fluid is located, there's different concentration of ions, that is in terms of acid or bases. And by definition, acid is any substance that yields hydrogen ions or hydronium ions when you dissolve it in aqueous solution. Aqueous solution in biochemistry mostly refers to water or water components, and bases on the other side are substances that yield hydroxide ions. So this is how we write hydroxide ions here. So now we say that our body has fluids, intracellular and extracellular, and in these solutions or in these fluids, we have different components of acidity and basic or alkalinity states. So for this purpose, it means our body needs to work in such a way that we maintain a balanced state that gives us a narrow pH range. And by pH range, we mean a narrow difference in terms of level of acidity. These are the systems in our body that will help us maintain the normal pH. And this is where it takes us to the buffer system. But how are they going to help us maintain this normal pH? First, they'll be maintaining this by reacting with strong acids or bases to changing them to substances that greatly do not change the pH. So they maintain a normal pH range in our body system by reacting to strong acids or bases to ensuring that there is no great change of difference in our pH levels. In short, buffer systems help us to prevent acidosis and alkalosis. So the systems is made up of a combination of either a weak acid or a base plus its salts. So these salts and acids and bases are the ones that will be reacting with the different compounds that are changing our pHs in the body system to prevent or to resist the change in the pH. So buffer system are like these good guys who help us prevent the excess in acidity or the excess in alkalinity of a solution. How? By reacting to these substances and lowering either the pH or raising the pH to acquire these normal pHs that we need. So it's supposed to help us maintain a balanced state of our pH in the body. So there are major types of buffer systems that are supposed or actually act in our body to maintain a balanced state of solution, and one of it is the protein buffer system, and it's said to be made of amino acids and hemoglobin. But then we have the phosphate buffer system, the bicarbonate carbonic acid buffer system, and the physiological buffer systems. We will discuss each of them one by one, so keep it here as we go and start with the first one. So let's start with the hemoglobin buffer system, which is the protein buffer system. So we both know hemoglobin is the compound that is known for helping transport both carbon dioxide and oxygen in our body system. So mostly with hemoglobin, it helps us maintain the pH. Number one, by combining with carbon dioxide to transport it in the form of deoxyhemoglobin, or by combining with oxygen to help us transform it in the form of oxyhemoglobin. Now, to bring us to our understanding, we need to know that when the blood is very acidic, that is, now it is in the state of acidosis, it means our blood has a lot of carbon dioxide that is existing in the system. So what happens is we want to eliminate this state of acidity. So what our hemoglobin will do, it will bind to most of this carbon dioxide gas and transport it to our lungs to release it as a process of a breathing out or expiration. So now when there's this pH change, either due to excessive carbon dioxide or due to accumulation of oxygen in our blood system, our hemoglobin will help us balance this by performing the hemoglobin buffer system by either binding to oxygen or binding to this carbon dioxide. So now what this hemoglobin does, it brings some effects onto how our carbon dioxide levels are or our oxygen levels are in the blood system. So I want us to go and see how these systems change or this effect come about. So here is how the hemoglobin works. So I've mentioned that as the hemoglobin attaches and binds to the oxygen and carbon dioxide, there are these different shifts that happen. So you need to understand that here we have the black one, which is showing the balanced state of our dissociation of carbon dioxide and oxygen, of carbon dioxide and oxygen on the hemoglobin level. So we have two curves. We have the blue curve that we are calling the right shifted curve, and then we have the left curve that we are calling the left shifted curve. So when does the dissociation curve shifts? So with dissociation curves, we're talking about a curve that is showing the change of hemoglobin saturation in terms of oxygen, and on the other side, that is the horizontal side, we are looking at the partial pressure of oxygen in our blood system. So it's being said that on the right shift, or on the left shift, that is the red curve here, it's being said that we tend to have a left shifted curve when our hemoglobin has an increased affinity to oxygen. That means we have oxygen levels increasing in our body system, but there's a reduced oxygen delivery to tissue. So I want to understand, the more oxygen is binding to our hemoglobin, the more less of it is not going to our tissues. But what can make this hemoglobin to be more affined to, what can make our oxygen to be more affined to hemoglobin? Number one, we are being told that this can be caused by high pH levels where it is more basic. So when there's basic state in our pH, then it's being said that most of the oxygen will have to be bound to hemoglobin so that we can at least lower the pH so that it can at least go to the expected levels. But again, you can have other state like low temperatures, low blood pressure, fetal hemoglobins, and so many other factors that can bring it in. But the curve tends to shift to the right. Okay, so the curve tends to shift to the left, where the hemoglobin tends to be more affined to the oxygen. So it means our blood is basic, and what is happening is our oxygen in this case has to be bound more to the hemoglobin so that we can lower the pH, to go to that required level of 7.4, so that it doesn't weigh more on the basic state, what you're saying, the alkalinity. But now we have the right shift or the right shifted curve. So it's being said that our curve will shift more to the right, where we have a state whereby there's a reduction on oxygen affinity. So in this case, it says our hemoglobin tends to release our oxygen more to go to the tissues. Why is it happening like that? It happens like that in that there's a case whereby the blood is becoming more acidic. So as a result, we want our carbon dioxide to release this oxygen so that it can go and be released to the tissues or to oxygenate our tissues. Why? Because there's high chances of too much carbon dioxide in our system that needs to bind, okay, to the hemoglobin so that it can be taken outside. And more factors can bring this. So the shift is to the right where there's acidity in our blood, while the shift is to the left where there's more concentration of oxygen in our blood. So instead you can say the right shift is due to acidity, while the left shift is due to alkalinity. But the oxygen dissociation curve is simply reflecting on how the hemoglobin becomes less affined to to oxygen when it is acidic, while the hemoglobin is more affined to the state when there is alkalinity. And that's how you can summarize it. But what does the oxygen dissociation curve brings as an effect? It brings two effects. One is known as the Halden and the other is known as the Bow effect. These two effects are reflecting again how the concentration of oxygen in our blood will affect the affinity for either carbon dioxide or oxygen. So the Halden effect is said to describe how oxygen concentration in the blood, okay, will determine the hemoglobin affinity for carbon dioxide. So they say that when our oxygen levels are so high in the blood, that is, you know, there is a excessive concentration of it, or there's a state whereby maybe the oxygen is low and so on. So it's being said that these changes of oxygen concentration in our blood has an effect of our carbon dioxide affinity. Our hemoglobin changes its affinity to this carbon dioxide. So Halden simply means hemoglobin affinity for carbon dioxide. But what is causing these changes of affinity is the level of oxygen in our blood. For example, if oxygen is highly concentrated in our blood, then what happens is our affinity for carbon dioxide or hemoglobin affinity for carbon dioxide will become low and it will bind more to oxygen so that it doesn't make the blood alkaline. But now there's the other aspect where we are saying if oxygen concentration is very low, then carbon dioxide levels will be high. So in this case, affinity for carbon dioxide will be high, bind more to it and release it out. That's how these affinities are changing. But we have the bow effect, which is describing on the opposite side. We're saying it's describe how carbon dioxide will affect the affinity for hemoglobin. So B will be talking about oxygen, hydrogen released in the tissues. So with the bow effects, there's an effect whereby a B is for binding, okay? Binding oxygen, hydrogen released in the tissues. It's saying whereby if we have high carbon dioxide in our blood, then hemoglobin will bind more to oxygen so that we can release it to the tissues and allow to dilute the acidity state in our blood. So these two are working in such a way that the concentration of one gas is affecting the concentration of the other gas. So number one, the Halden effect here, it's where oxygen concentration will affect the hemoglobin affinity for carbon dioxide. While here, the carbon dioxide concentration is going to affect our hemoglobin affinity for oxygen. So you can see how all this is working. Carbon dioxide affecting oxygen, that is Bow's effect, while on the other side, Halden is affecting carbon dioxide. If you're so confused, just look at how these two gases, the short form of these two effects. Halden has carbon dioxide in it. Bowl has oxygen in it. So in the first one where there's carbon dioxide, that is in Halden, here we're talking about affinity of carbon dioxide. Well, in Bohr, where we have oxygen, then we're talking about oxygen affinity. So that's how you can easily get these two handled. However, all this is coming from the hemoglobin as a buffer system for regulating the acidity and alkalinity in our blood system. But then we have the second buffer system that we call the phosphate buffer system. So the phosphate buffer system is said to play a role largely in eliminating hydrogen, however, using the kidneys. So in this system, we have what we call the acidic phosphate ions and the alkaline phosphate ions. So what these two ions do, they react to produce a reaction we are calling neutralization, so in such a way that there'll be acid-base balance by whereby if the blood is too acidic, then the alkaline phosphates will react with this acid and neutralize it and take the pH to the normal level. However, if the blood is so alkaline, then our acidic phosphates will come in, react with this acid, react with this base and neutralize it and take our pH to the normal levels. So these two buffer system, they react intracellularly, but it also works closely with the renal tubules. So maybe you may ask yourself, what are these components of the base of the phosphates that you're saying the one phosphate is acidic, the other phosphate is alkaline? So the acidic buffer component of our phosphate system is what we call the dihydrogen phosphate. Dihydrogen phosphates. This is the acidic phosphate that will react with the alkaline ions that are making our blood alkaline. And in this case, when it reacts, it will achieve what we call neutralization and take our blood values or our blood pH to normal. But again, we are saying we have a basic or an alkaline phosphate that also participates in this process. And in this case, we are calling it the hydrogen phosphates. So the hydrogen phosphate is the alkaline buffer of this phosphate buffer system that will react with the acid in nature if our blood is acidic and take it to the normal values to bring our blood to a normal value. So literally the way we are saying buffer systems are working between acid and bases to take our blood pHs to normal values. So if it is acidic, then the base will react with it. If it is alkaline, then the acid will react with the alkali and bring it down. But again, we have the third buffer system, what we call the bicarbonate carbonic acid system. This system is self-explanatory. It just tells you it has a bicarbonate, it has the carbonic acid. So remember, in any buffer system here, we're talking about an acid being present and a base being present. So that in the state where our blood is acidic, then the base will react to the acid, neutralize it, and take the pH to normal. If the blood is very basic, then the acid will react with the base and take the blood to normal. So the bicarbonate carbonic acid buffer system consists of the carbonic acid here and it consists of the sodium bicarbonate. So it has these two. So now how do we end up with these two components? It's being said that these two components originate from the carbon dioxide gas. So we know in our body we have all these processes that react and produce carbon dioxide as the waste gas. So carbon dioxide is very unstable. So what it does when it exists in aqueous solution and specifically water, it will form for us carbonic acid. So what this carbonic acid it will do, it will dissociate into hydrogen ions and it will dissociate into bicarbonate. So this is our reaction here. So we have carbon dioxide reacting with water to give us the carbonic acid. But the carbonic acid is a bit unstable and it will dissociate into hydrogen ions and the bicarbonates. So here we have an acid, we have a carbonates. So what happens is when the blood is acidic, then you can have the bicarbonate reacting with this acid and neutralizing it. However, if the blood is very basic or alkaline in this case, then the carbonic acid can react with this base, neutralize it, and take the blood to normal levels. So with this system in existence, it means our respiratory system plays a very big role in ensuring that this carbonic buffer system is very present and stable and putting everything into place. So for example, if we need we need the carbon dioxide gas, it means we get this from our lungs, during the inspiration and respiration, we get our carbon dioxide gas in and it can dissolve to give us the carbonic acid and the bicarbonate. But when it comes to the bicarbonates ions, it's being said that it has to be regulated mostly by our kidneys, because that is where also we regulate most of our ions. So the regulation of bicarbonates are done primarily in our renal system or in our kidneys. But you just need to remember, for us to have the bicarbonate carbonic acid buffer system, it's established through the existence of carbonic acids and the sodium bicarbonates, which are mainly coming from carbonic acid, from the carbon dioxide gas that will dissolve in water to give us carbonic acid, which will dissociate to generate hydrogen ions and bicarbonates. And the last one, we are talking about the physiological buffer system. Physiological buffer system, they refer to what our body system has that is promoting physiologically in establishing a balanced acidity or alkalinity in our system. So let's start with the lung or respiratory system. It's being said that the lung and the respirations are like the quickest way to help respond to any changes in our acidity or alkalinity, and most of this is eliminated, or it is maintained via the respiratory gases, that is oxygen and carbon dioxide. And to just remind us, here we will be working with two things. Number one, we will be working with carbon dioxide, which of course, remember, it's dissolved in water to give us carbonic acid and the bicarbonates. So now with the carbon dioxide having that, then it means it promotes largely in establishing the bicarbonates carbonic acid buffer system. However, we have the oxygen that is also part of our respiratory system. And reminding ourselves about oxygen, it means there is closely an involvement with the hemoglobin compounds. So hemoglobin coming in here, this takes us back to our Bohr effect and the Halden's effects, meaning the lungs or the respiratory system is a major component of our physiological buffer system. But let's not leave it here. We have another system that forms part of this physiological buffer system, and that is the kidney and the metabolic systems in our body. So the kidneys reminds us of the existence of the phosphate buffer system. That in the kidney we have the existence of those sodium phosphates, that closely work together to act with the acid and the bases to eliminate it. And this system is very effective, although it is a bit slow because it takes like hours or days to correct pH changes, but it's one of the systems that works together to establish this. So that was all about buffer system, discussing the four systems, that is the physiological buffer system, discussing about the bicarbonate, the bicarbonates, bicarbonates, carbonic acid, and then talking about the phosphate buffer system and the issue of the hydrogen. I'm sorry, the hemoglobin buffer system. So all these work together to just bring these pHs down and balance, and to avoid our body from becoming too alkaline or too acidic, what you call preventing it from establishing acidosis or alkalinity or alkalosis. That was all. If you like this channel, guys, just subscribe, share with your friends. Welcome also to be part of this family. We will share more content here, and it will be varying each and every time. And like I said, if you love, you can make notes, you can share with your friends, you can suggest which topics we can do next. And that's it for today, and see you in our next sessions. Bye bye.